Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Welcome to module number 5, machine learning for time series forecasting. I'm going to do this module in 4 parts. In part 1, I'll start with basics and fundamentals of machine learning. Especially for those of you who don't have a background in machine learning, I highly encourage you to watch this video very carefully. In part 2, we will talk about the winning models when it comes to time series analysis using machine learning. Because if you have watched my previous videos, you know that in the world of machine learning, there are dozens of powerful models, including KNN, SVM, penalized regression, and you name it. But the ones that works in practice when it comes to time series analysis are the decision tree based models, and more specifically the more advanced ones like XGBoost, CatBoost, and LightGBM. We're going to talk about how they are different from each other and how successful they are when it comes to the forecasting time series analysis. Then in part 3, we will talk about the challenges in time series when we're doing machine learning. We will see how machine learning basically is able to handle non-stationary data, or we're going to talk about the seasonality and limited data in general when we have time series. And most importantly, we're going to talk about cross-validation and bootstrapping. What are the right ways of doing cross-validation and bootstrapping when we have a time series data set? Because we know that we cannot simply shuffle the data, and if we do that, there are some things we need to be very aware of, and we have to do it correctly when it comes to time series. The idea is that we cannot blindly apply any machine learning model to a time series task. We have to prepare the data set first, and we have to consider all these challenges. Then finally, we're going to do all these things in Python. So this is the part 4 of module 5 that I'm going to go ahead and show you how you can basically do a time series forecasting analysis correctly in Python. We're going to do it from scratch. I'm going to use scikit-learn package, and basically I'm going to show you how you can replicate an automated time series task using PyCaret, but building that thing using scikit-learn. Okay, so I hope you're going to stay excited through this relatively longer module. Now, without further ado, let's dive into that. Module 5, Part 1, Machine Learning for Time Series Forecasting Basics. Let's start with model comparison. You have seen this slide in our module number 1 when I was comparing econometrics model versus machine learning model versus deep learning models at a high level for a time series task. But here, I want to specifically focus on these two, namely econometrics and machine learning, especially because you have watched module 3 and 4, you're quite familiar with ETS and ARIMA models in general, so you should have a better understanding when you look at this table now. So starting from feature engineering, this is what we want to compare between the two models, right? We saw that in ETS model or in ARIMA model, we were required to explicitly model basically the seasonality or trend. Now, for example, our ETS model was looking at, 3 components. Look at level, look at trend, and look at seasonality. And we call it triple exponential smoothing model to basically capture that seasonality and trend, right? Or in ARIMA model, we looked into the previous lags. We said, okay, how many lag components should we include in the autoregressive? How many moving average components? How many lag terms of the error term should we include in the model? And how many times do we need to integrate the model, right? How many times differencing? So this was completely basically done manually, right? This was explicit modeling of seasonality or trend, if you want to say. However, for machine learning, the story is a bit different, right? We're supposed to capture the complex pattern with less need for manual engineering. I'm not saying that we're not going to do some data pre-processing. We are. We're still going to include some lag terms. We're going to transform our simple time series to a supervised machine learning task. But we are not going to specifically or manually model the trend or seasonality. So basically that trend or seasonality is going to be captured by complexity of the model, right? But again, this is going to be a mix. It's not going to be completely automatic. It's not going to be completely manual. So this is where the machine learning is. Then for model complexity, the econometric model is simply, they're less complex because we have functional forms. Look, remember the ETS and ARIMA, there was a specific functional form, and then we were mainly focusing on data generation process, right? So it's less complex compared to machine learning. And when I say machine learning, I'm talking about those models that we cover for time series tasks, right? Basically, let's say decision tree based ones, right? Or boosting models. These are relatively more complex models with the hope that it can capture more complex patterns in the data. When it comes to interpretability, our ETS and ARIMA model are perfectly interpretable, right? You know all the parameters, you know all the components of the model, and you can say, for example, this autoregressive part is doing what? That level or that seasonality or that trend component in ETS model is doing what, right? However, in machine learning, that interpretability is going to be moderate, right? It's not going to be high. I want to label it as moderate simply because it means that yes, at the end of the day we might use feature importance, for example in random forest or XGBoost, and say which feature had the most impact, right? For example, lag number one, what was the impact of lag number one on the entire thing? We can show the magnitude, but we cannot quantify it, right? We can say, for example, no, including two lags, lag one was more important than lag two, but we cannot quantify it. We cannot say, for example, what was the exact impact of this feature in the model on the target variable. So that's why in terms of interpretability, the machine learning is moderately interpretable compared to econometrics. Computational intensity, obviously, econometrics models, again, there's a closed form solution for that, and then for that reason, it's going to be computationally less complex, right? Not for all the econometrics model, but again, there's a functional form, there are formulas, you can use them, and the optimization is going to be pretty more straightforward compared to machine learning models. So for machine learning models, again, for the ones that we cover for time series analysis, like boosting methods, they require more computational power. Data suitability. So econometrics model basically works well when the underlying process is well understood. So this is really important. I think I can speak to this right now more compared to the first couple of lectures, right? Because now you're familiar with ETS, you know what is ARIMA, you know what is econometric model in general is, and if you have a well-behaved data set, like our airline passenger data set, which was like this, the idea is that if you see a well-behaved data set like this, go ahead and use econometrics. Do not necessarily waste your time with more complex models like machine learning or deep learning models, because this data like this is screaming at you that there's a trend, there's a clear trend, there's a clear seasonality, and your classical econometrics models, ETS, ARIMA, are going to shine. They're going to perform perfectly. And you don't, most importantly, you don't need tons of data, right? I think if your data set is well behaved, maybe, I don't know, a couple of dozens or 10, 20 observations is good enough. But can you imagine that you can get a good deep learning model with 20 observations? So always keep in mind, in time series in general, we have limited data, right? And if for whatever reason you're working with annual data and you have only 40 observations, so most probably, and if the data set is well behaved, you will be better off going and focusing on econometric models and don't waste time in machine learning and deep learning. So I really want you to understand these things at a high level, and then before jumping into modeling, decide which class of models is going to perform better. Obviously, the machine learning models are more suited for basically more complex relationships. Again, if I have something like this, the airline passenger data, I'm not going to use machine learning. But if the trend is not that clear, or if there's a regime shift in the data, or if the seasonality is not regular, or something like that, then I'm going to consider more advanced, more complex models like machine learning. Yeah, that's pretty much it. So now with this background, let's go ahead and get into the data preparation part for machine learning. All right, pre-processing time series data for machine learning task. Basically, how do we convert time series problem into machine learning supervised problem, right? So let me give you a little bit more context. On the left, we have our very well-behaved time series, which is airline passenger. And on the right, we have our most not well-behaved data, like Apple stock price, right? So what do we have? How does the time series data look like? Again, this is nothing fancy. I'm going to try to give you some context here. So we have quarterly data here. This data starts from, let's say, quarter 1, 1949, all the way to, I think, 1960, quarter 4, right? So at the end of the day, your target variable is something like this, y1, y2, all the way to I don't know, I think this data set we have 144 observations, right? So this is your time series. This is your data, a single column data. And we're focusing on univariate time series, right? So I'm not talking about external features. This is just univariate time series. And so this is the data. The same story for the right-hand side data set, right? So when I have Apple stock, let's say this is daily return, daily price from January 2020 all the way to sometime in 2024, right? So again, the data set is going to be something like this. This is daily data, right? So here, this is quarterly, this is daily. And the same idea, y1 all the way to whatever days, 1,300 something, right? So then I'm just making up these numbers. But the idea is that at the end of the day, this is your time series. We saw that in econometrics, basically we had, for example, we had ETS, we had ARIMA. How did we handle this? We said, okay, let's go ahead and create some lag values and add it as AR components. Let's go ahead and bring the previous errors as moving averages, to number 1, number 2, and etc. For ETS, we modeled the level specifically, we modeled the trend, we modeled the seasonality. So this is how we handle that in econometrics. How do we do it in machine learning? So how I transfer this single column of data set into a proper data set for a machine learning task, right? Remember, what do we need for machine learning? We have some features. This is your features X, and you have a target variable Y. So what are these things? Let's talk about them. Okay, let's look at a very simple example. Imagine we have 1 year of data, and the data is monthly data, right? So how many observations we have? It's going to be 12. Again, I'm going to keep it super simple. Imagine something like this. Month 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Something like this, right? So this is your monthly data, and we have observation from number 1 all the way to number 12, right? And then this is your data set going from Y1 all the way to Y12. So what do we do? Imagine, I would say, let's use the 4 month of data to predict what happens in the next month, 5th month, right? So if I want to do something like that, so I'm going to use the 4 observations here, 1, 2, 3, 4. So 1, 2, 1, 2, 3, 4, and make a prediction for this one, right? So, and then I'm going to roll it over. So basically, this is what we're going to do. We say use observation here. Let me show it to you. Number 1 through number 4, make a prediction for number 5, right? Use observation number 2. So this is, we're rolling it over here. Number 2 all the way to number 5, make a prediction for number 6, right? So what is this? I want you to basically pause the video and think about it. What are these things? How can I label them? So imagine if I'm here, let me use another color. If we are here at day 4, at month 4, right? T is equal to 4. Then, so basically, I can show it with my YT. So this is going to be my YT. And then what is this one? This is going to be YT minus 1, right? Yeah. What is this one? This is going to be your YT minus 2. What is this one? YT minus 3. So basically, I'm adding 3 lags, right? So I have YT and then 3 lags, lag 1, lag 2, lag 3. So this is going to be my features, right? So I have, look at that. I'm transferring this thing into set of features. What are the target variable? The target variable is your YT plus 1 in this case, right? So this is going to be your YT plus 1, that's your target variable, and the rest are your features. So why did I pick 4? It was just arbitrary number. I can use more lags, but remember, if you use more lags, your degrees of freedom is going to decrease, right? So you cannot have 8 observations here, right? So here I could have 8 observations because the lag was 4. If I use higher lags, so obviously I'm going to have fewer observations. But the thing is that at the end of the day, we transform this single column data set, which 12 observation, into this supervised machine learning data set with 8 observations. So 8 observations, because we need to, again, here simply because we added 3 lags. So we need to have features, and targets. So I really want you to pay attention to what happened here. Again, a single column data with 12 observations became into something supervised machine learning data set with 8 observations. Now we have features and target. All right, now let me show you how we can create those supervised machine learning data sets for different forecasting strategies. So you have seen this slide before, and then let me actually quickly review this one because we're going to need the terminology from this slide going forward. So at the top, we are going to see our one step ahead forecast, right? So this is our one step ahead forecast. This is our multi-step ahead forecast. Let me see if I can write, yeah, multi-step ahead forecast. And this is our multi-horizon or multi-output forecast, right? So again, this is a quick reminder. The purple one is the actual data, and this one, this is a lighter pinkish one is a current forecast, and the green one is the previous forecast, right? So what was this one step ahead forecast? We said this was pretty straightforward. We said, for example, we are at time step t. Imagine this capital T is equal to 4, and these are 4 days, right? If you wanted to predict what happens in day 5, you needed to use 4 days of information to make a prediction. If you wanted to predict what happens in day 6, you had to wait 1 more day and collect 4 observations and make a prediction for day 6. If you wanted to see what happens in day 8, again, you have to wait 3 more days to collect data and make a prediction, right? So this was one step ahead forecast. At each point in time, we needed to have access to the previous data set to make a forecast in one step into the future. Then we said that we can do these things iteratively and use the previous predictions to make a prediction for the future, right? So we call it multi-step. So for example, we said, what if you want to make a prediction for the next 4 days right now? You know, we are at day 4, you want to make a prediction for the next 4 days. We said, okay, let's do it iteratively, step by step. In a step 1, make a prediction here. In a step 2, use that prediction. In a step 3, use the 2 predictions, right? In step 4, use all the predictions. So there you're going to use this one to come up with a prediction for this one, right? So this is if you wanted to do it one step ahead forecast or multi-step ahead forecast. In both of them, as you can see, your model requires one output. So I'm going to call these two single output. So single output. So this means that here there's only one output that you're predicting, and that's y(t + 1). I can put a hat on top of it and you see that this is a prediction. So this is a single output, y hat t + 1 at each point in time. Either we're going to do it the one step ahead or we can do multi-step ahead. Okay, hopefully you know the difference between the two. And then we said that there's another type of forecasting that you can do multi-output at the same time, right? So I'm going to call this one multi, as in it, well, again, this is multi, we can call it multi-horizon or multi-output. But the idea is that you're at day 4 and we're going to predict what happens day 5, 6, 7, and 8 right now at the same time. We're not using any predictions to feed it to the model like multi-step, right? So multi-output, this means that you're predicting y hat, in this case, y hat t + 1, y hat t + 2, y hat t + 3, and y hat t + 4. So as you can see here, we have 4 target variables. Here we have only 1 target variables. Now I'm going to show you how we can prepare a univariate time series for different tasks, right? For different forecasting tasks. Either it is single output or multi-output. All right, let's start with the supervised data frame for a single output, right? So we have seen something like this. I just added some extra term here. We know that on the left we have our features. On the right there is single output. There's only one output that we're predicting. And pay very good attention to the colors and notations here. The black ones, these are actuals. And the purple ones are prediction. Again, this is single output, one step ahead. This means that if you want to predict y14, you need to have all the data for the past 4 days. y13, y12, y11, y10. And these are all actual data. Look at that, they're all black. So these are actual data. So then we're going to say, let me actually label them. So this is going to be my yt, and lag 1 is yt minus 1, lag 2 is our yt minus 2, and lag 3 is our yt minus 3. And what is the target? It's lead 1 yt plus 1. Okay, so this is basically if I want to create from a univariate time series a data frame which is supervised using 3 lags, this is how the data set is going to look like, right? And again, this is single output. There's only one yt that we're predicting, and this one is one step ahead. How do I know it's one step ahead? Because look at that. If I want to predict y14, I'm using all the actual information in the past 4 days. On the next slide, we're going to see the exact same table, but for multi-step ahead. I want you to pay attention to see what happens to the color, well, actually something like this, to the color of these observations. They're going to go from black to purple. Why? Because we know that if you want to, for example, predict y6, you need to have a y5. Where is this y5 coming from? It's coming from this prediction, right? So this is for the next slide. Okay, so this is what I was talking about, right? Again, we're having single output. So this means that there's only yt plus 1 output that we're predicting. Again, I can put a hat on top of it or not, but you know, you get the idea. All these purple ones are the predictions, right? And then we have our regular yt minus 1, yt minus 2, and yt minus 3, right? Okay, so pretty much the same setup, but the only difference is that now if I want to predict y14, I don't need to wait until y13 comes. I can basically do it with only 4 observations, right? If I have only 4 actuals from y1 to y4, I can make prediction for y5, and then I'm going to use that one along the past 3 days. Imagine this is daily data. To make y6, use that one along the past, predictions to do y7 and etc., right? So I want you to pause the video or go backward and see, go to the previous slide and then compare the colors here, right? Remember, the black ones are actuals, the purple ones are predictions. But the point is that regardless of if you're doing one step ahead prediction or multiple step ahead prediction, this is a single output. This means that your model is predicting one output for each observation, right? So this is exactly what we did using econometric models, right? For example, we have ETS, we had ARIMA, or any kind of simple linear model, right? Econometric model is doing this, right? You can, at the end of the day, it's going to go ahead and create this y hat t plus 1 for you. And I think I briefly mentioned it in our module 1 as well, that not all the models are able to do multi-output. And I'm going to talk about it in the next slide, why, right? By multi-output, I mean y hat t plus 1, y hat t plus 2, y hat t plus 3, all at the same time. And I'll explain it in detail why econometrics models are not designed to create those multiple outputs. We can synthetically create those ones, but it's not efficient. And I will explain to you why. Now, let's look at a case for the multi-output setup, right? So here, the only difference between this one and the previous one is that, actually, look at that. The features are pretty much the same. Let me go ahead and label them again. So these are the features. I have yt, this is yt minus 1, yt minus 2, and yt minus 3. So the features is pretty much the same, right? The only difference is that here we have multi-output at the same time for each observation. Look at that. I have, let's say, 10 observations here, going from number 1 all the way to number 10. And then I have 3 output for each observations. So I'm predicting, let me try, go ahead and use, let's say, green. So this is my yt plus 1. Again, I can put a hat on top of it. You know that is a prediction. Y hat t plus 2. This is lead number 2 and lead number 3. Remember, lag versus lead, right? Y hat t plus 3. Right, so I'm predicting these 3 time steps ahead at the same time. So this is multi-output. For example, if we are at, I don't know, observation number 10, and we have the past days of information, y13, 12, 11, and 10, I can predict the next 3 days at the same time, right? So y14, y15, and y16, look at that, these purple ones are the predictions. So this is a difference between multi-output and single output. But why am I highlighting these things here? Because for 2 reasons. Number 1, you know that how we can transform a univariate time series data into a supervised data set for machine learning. So that's number one. Number two, I want you to appreciate why machine learning models are capable of doing multi-output prediction at the same time, and not all the econometrics models are able to do that. Actually, none of them are able to do it directly. But let me try to present this case to you. I'm going to go ahead and use another color. Let's do purple. Imagine I want to use econometrics like ETS or ARIMA to come up with these multi-output models, right? So the features are pretty much the same. So I can use this data set as features. And then it seems that if I want, let's say I'm going to use the past 4 days. Guys, look at that. This is super simple. Don't overthink it. I'm going to pass the 4 days of information to an ETS model, and it can perfectly predict next day, right? So this is going to be my label number one. I can go, so I have, let's say, ETS model number one. So the model is the same. Let's say, let's call it ETS, whatever, or linear regression, right? So, or ETS or ARIMA or whatever. So I have one model, and I'm going to train it on target when the target is y hat t plus 1. So this is one ETS model, right? If I want to use the same observations, y1 through y4, again, for the same lag values, and make a prediction for y hat t plus 2, I can do that. I can literally train another ETS model. The features are pretty much the same, 3 lags, y1 through y4, y2 through y5, y3 through y6, and etc. And now instead of predicting y hat t plus 1, we're predicting y hat t plus 2. I can still do that. I can use this feature to make a prediction for this, right? So again, I use these features to make a prediction for y hat t plus 1, for y hat t plus 2, and the same story for y hat t plus 3, right? So I can do that. I can perfectly do that. There's nothing wrong with that, right? So, but the idea is that for each, so first of all, I'm training 3 different models. Well, model is the same, ETS, but I'm training it 3 times. So it's going to give me 3 different sets of parameters. Because the target variable is simply different, right? Once I'm predicting what happens tomorrow, another model I'm predicting what happens in 2 days, another model I'm predicting what happens in 3 days. So basically you can do that. So technically, theoretically, you can do that. You can use econometrics to create a multi-output forecast. But as you can see, what if that multi-output, what if you want to predict 30 days into the future at the same time? So this means that you have to run your econometric models 30 times. You have to train them 30 times. And then, as you can see, it's not going to be stable. It's not going to be efficient. And more importantly, if you increase this longer horizon, for example, if you go from 3 to 5 to 10, if you're predicting let's say, y hat t plus 10, you're not using information from y hat t plus 1 all the way to y hat t plus 9, right? So you're skipping that information. What if the data set is non-stationary, or there's a clear trend and you don't want to miss that, right? So for that reason, we say that econometric models fundamentally are not designed to generate or to forecast multi-output at the same time. However, this same task is pretty straightforward using a machine learning model. Let me show you to you on the next slide how it's done. All right, now let's see how it's done using a machine learning model, right? How machine learning models, and later on we're going to see deep learning models, are capable of doing multi-output prediction at the same time, right? So I'm going to go ahead and rewrite this y hat t plus 1. So the goal is to predict y hat t plus 1, t plus 2, and y hat t plus 3 at the same time, right? So we noticed that on the previous slide, it's not possible using a econometric model. It's not possible for all the machine learning models. For example, linear regression is some sort of machine learning model, or again, depending on how you're looking at the problem. But linear regression is not suited for multi-output, simply as we explained it in the previous slide, right? But some decision tree based models, these are machine learning models, are perfectly suited for creating multi-output forecasts, right? So imagine you have a decision tree, right? This is your decision tree. And the idea is that, I don't know, at each terminal node, instead of looking at a target variable, instead of looking at, for example, y hat t plus 1 or yt plus 1, you're going to look at a vector of values, right? So basically, you're going to look at the vector of predictions instead of a single value. So each leaf in the tree is associated with a vector of prediction. So for example, this is, I don't know, I'm going to the right branch here, and I'm going to associate a vector of this prediction. In this case, y t plus 1, t plus 2, and t plus 3 to this terminal node, right? And then the rest is pretty much the same. You know, we're going to go ahead and calculate the residuals and then sum them up, square them, sum them up, and then come up with a cost function. The setup is pretty much the same, but the difference is that a decision tree based model is able to look at a vector of predictions at a terminal node instead of a single value. And with that, it can do multi-output. It can do multi-prediction at the same time, right? So this is for machine learning. And all the decision tree-based models, including random forest, XGBoost, LightGBM, CatBoost, are able to do multi-output as well as single output forecast. For the deep learning, when we get to the deep learning section of the course, you're going to see this is pretty, it's more straightforward. You know, you have a neural network, I don't know, you have a bunch of features, and you have a couple of dense layers. And at the end of the day, instead of only having one node, you can have 3 nodes. That's it. So this can be yt plus 1, yt plus 2, and yt plus 3. So remember, guys, all these things are labeled, right? So we have a set of labeled targets and labeled features, and we're going to train models, and then we're going to figure out the coefficients, the weights, and etc., etc. So this is hopefully it makes more sense now compared to module 1 when I said that not all the machine learning models or not econometrics models are able to do multi-output forecasts. Hopefully it makes a lot more sense now. All right, this is all I needed you to know before I move forward and talk about the details of how we can do a time series forecasting task using machine learning. So for the rest of this video, if you have zero background in machine learning, I highly encourage you to stay with me. But if you think that you're quite familiar with the concept of machine learning, you know how machines actually learn, and you don't need a refresher, you can skip through the next video. Okay, so let's switch to the review mode, and this is what I'm going to cover in the next 40-45 minutes. Machine learning fundamentals. We're going to start with what is the difference between machine learning versus traditional programming. So what's the difference? We're going to talk about different types of machine learning. What is a model? What is a machine learning model? What are the parameters? What is parametric, non-parametric? All these sort of terminologies. We're going to talk about evaluation metrics. Obviously, for time series task, we're going to look into RMSE and a bunch of others. In the Python part, I'm going to talk about those details a lot more. We will cover the bias-variance trade-off, the concept of overfitting. I will discuss, how we split the data set into train, test, and validation set. We will talk about resampling methods, namely cross-validation and bootstrapping. I will talk about the cost function, because at the end of the day, when we talk about the concept of machine learning, it's not pure the magic, right? We have to set the scene. We have to come up with a cost function, and at the end of the day, there's optimization going on, right? So through that optimization, the model is able to figure out what are the best set of weights, what are the best set of parameters, and etc. And we're going to talk about the concept of solvers. We talk about gradient descent and a stochastic gradient descent. And then finally, we need all these things to be able to answer this simple, exciting question. How do machines actually learn? So if you think that you have a solid background and solid understanding of all these concepts, feel free to skip the rest of the video. But if you think that you want to hear it one more time, just bear with me and I'll see you on the next slide. Okay, so what is machine learning? Machine learning, as we talked about it in the previous modules, is a subset of AI that enables computer to learn from the data. Okay, so this is different from the traditional or classical programming in a sense that, look at this one. This is classical programming. In classical programming, the inputs are some data and some rules. So for example, you have been given x and some rules. So let me show it with f of x, right? So this f of x can be anything. Let's keep it very simple. It's equal to x plus 3. So I know the x, I know the rule, and then the computer is going to do the math and it's going to calculate the output, right? So for example, and this output I can label it as y. For example, if x is equal to 3, or let me use a different number. If x is equal to number 6, then the output is going to be 6 plus 3, which is equal to 9, right? So this is classical programming. There is no uncertainty. The inputs are given, the rules are given, the computer is going to do the math and give you the output, right? However, in machine learning, the story is different. You have been given some inputs. The input can be X's and answers, right? So the in depending on the type of machine learning, sometimes you will be given the answer, sometimes you won't. This is the difference between supervised versus unsupervised. But let's keep things simple. So imagine you have the X's, you have the Y's, and the goal of machine learning is to learn from the data, right? So this is the goal, to learn from the data. What are the rules? What were the relationship? What was the underlying pattern between X and Y? So that's the goal. The goal in machine learning is to estimate this f of X. Let's show it with f hat of X, right? So this is the pattern. This is what we're looking for in machine learning. Okay, so as we said, so this means that the machine learning system is trained with a bunch of rules and algorithms. So it is trained rather than being explicitly programmed. So whenever we say that machine learning is a system that's not explicitly programmed by human, this is what we mean. However, this does not mean that it's not human involved. We, the humans, are the ones who are going to set the scene, who are going to set the rules or algorithms. Okay. Now, we know that machine learning involves in automated detection of these patterns in the data and apply those patterns to make some predictions, right, on the unseen data. So the optimal goal in machine learning is to maximize the performance of the model on the unseen data. So it's all about generalization. How good your model is in terms of generalizing of predictions on something that the model has never seen before. That's the optimal goal in machine learning. All right, now that we know what is machine learning, let's look at different types of machine learning. The most common one is called supervised. In supervised machine learning, the data is labeled. So what does it mean is that we have both X's and the labels of the X's. So whatever your target variable is, it is known. So for example, if you're doing regression analysis, if you're doing a housing price, you have the features and you know the price of the house as well. If you're doing classifications, you have the features and you know if a client defaults or no default. So you know all these things, and the machine is going to learn the pattern and come up with some predictions. And at the end of the day, you can compare these predictions with the actuals to just make the model better. If these errors are small, it's a good. If the errors are large, so we have to go ahead and make the model better. So that's the supervised. In unsupervised, the story is a little different. We only have X's. There's no label here. There's no target variable. And that means that the output is going to be a little fuzzy. So what are we looking for? So in unsupervised, usually we're looking for basically what is the underlying pattern in the data, in the inputs, right? We're looking for some representation of the data. So the examples are, we use unsupervised learning for clustering, anomaly detection, and dimensionality reduction. So imagine you have a data set with thousands of features, and you want to reduce the dimension of the data just because of for visualization, right? So you cannot visualize something in 1,000 dimension, but you can reduce the dimension, let's say, into two components. We can use principal component analysis, PC1 and PC2, and then do a simple visualization and see where the clouds of data are standing. Okay, so this is called unsupervised. The third one is semi-supervised. So semi-supervised is a combination of supervised and unsupervised. And the way that it works is like this. So you have, imagine these are your features and this is your target variable. And for part of the data, let's say for this part, we do have both the features and the labels. But for the, let's say, most of the time for the majority of the data, you only have the X's, you have the features, you do not have the labels. So the goal is to use machine learning models to figure out, based on this part of the data, to figure out what is the relationship, what is the pattern, and then apply that pattern to this part of the data to come up with some labels. We call it meta labels for this part of the data, which is unlabeled. And we're gonna then we can go ahead and use this meta labels to train the entire model. So that's for the semi-supervised. The next one is self-supervised. So self-supervised learning is a type of unsupervised learning. But it has the property that the learning process itself is being fed with the data itself. So what it means that, so let me give you an example. For example, you've been given a sequence of text and your job is to predict the next word, right? Or imagine you have an image and part of the image is blurry and you want to train the model based on whatever it is in the data set and to come up to replicate this blurry part, right? So this self-supervised is usually used in deep learning applications rather than machine learning. And the last one is reinforcement learning. So in reinforcement learning, there is this agent living in an environment. So we have an agent which interacts with the environment. The agents can take some specific actions. So we are going to define the actions. So for example, it can go up, down, left, right, or in stock market, it can buy, sell, or hold, right? So this agents there are going to be some specific actions that it can take, and it's going to take those actions to maximize a reward from the environment, right? So based on the reward, the agent is going to get feedback from the environment and then just repeat this process thousands or millions of times by doing random exploration and exploitation. Okay, so at the end of the day, the goal is by maximizing this reward function, the agent is going to learn something called policy function. At whatever state in the environment the agent is, what is the optimal policy? What is the best next move? So this is the output of the reinforcement learning, something called policy. All right, so this is at the very high level, different types of machine learning. And again, I assume that you have some backgrounds in machine learning, and this should be a quick review. Now we're going to go through some set of slides that help us explain how the machines actually learn. So we have to see what is that model, what are the performance metrics, what is bias-variance trade-off, and what is the cost function, and how do we optimize that cost function. So let's start by the model. So this is a simple machine learning model. A machine learning model is a function of some input variable and some parameters or hyperparameters. And of course, as we said, this is different from traditional programming. It means that it involves some uncertainty. There is no true model out there, right? So that's why we have to add this noise. The dimension of the data is going to be m, so we have m dimensional feature space and let's say k parameters and hyperparameters. So our y variables is sometimes called response variable, dependent variable. In machine learning language, we usually call it target. Our x variables, these are predictors, independent variables, and again, in machine learning language, we call them features. And thetas are our estimates or specifications or parameters of the model. Okay, so it's all about estimating this f by something called f hat. So this is the goal in machine learning for two purposes. One for inference, this is the interpretation part of the machine learning. The other one for prediction, how model is doing a good job in a never seen before data set, right? Okay, so now let's say we have a model. How do we quantify the performance of the model? So generally, if it is a regression, we're going to use some basic performance metrics like MAE, mean absolute error, MSE, mean squared error, root mean squared error, and this is root mean squared error, log error. Then we have R square and adjusted R square, and we can have again lots of different metrics as well. We can have MAPE, which is mean absolute percentage error. We can have SMAPE, symmetric mean absolute percentage error, and you name it. Depending on the model that we have, depending on the nature of the target variable, we may end up using different performance metric for regression. For classification, same story. The most important one is what we call confusion matrix, and based on that confusion matrix, we can go ahead and define bunch of or dozens of statistics, performance metrics like accuracy, precision, recall, F1 score, AUC, ROC as well, and again, entropy, cross entropy, Gini, and you name it. In the machine learning course, we have talked about almost all of these performance metrics, but the goal is that we come up with something that can quantify this measure of our error. What is the distance between the predictions and the reality? Okay. Now let's talk about a very important concept in machine learning, which is called bias-variance trade-off. So what we have here in the graph, on the horizontal axis, we have model complexity. As we go from left to right, the model is going to become more complex. For example, in linear regression, we start with a very simple linear function, and then we make it more quadratic to the power of 3, to the power of 4. We're going to add interactions and etc. We're going to make the model more complex as we go from left to right. On the horizontal axis, we have a measure of the test error. For example, if it is regression analysis, we can look at the mean squared error in the test set. Okay. Now, I want you to look at the graphs at the top, right? So if the model is too simple, We say that, let's say this is your train set and we are using the model, and let's say this is our estimation. The model is super simple. Actually, it's going to give you the average, right? So the idea is that this model is what we call, it has high bias. It means that if you repeat this process, if I worked with different subsamples and I use the same model, this on average is far from reality. It seems that in reality there is this curvature relationship in the data, but the model is not capturing it. No matter how many times you repeat it, on average it's not hitting at the target. We say this model has a high bias. So high bias, I can show it here. So the model has very high bias. This is a very simple model, but the variance is small. Model variance is small. What does it mean? It means that, again, if I use another subset of the data, maybe it's going to be a slightly lower, slightly higher, but on average we're not hitting at the target. So the variance is small, the bias is high. A combination of the two, which is, for example, a mean squared error in the test set, is going to be super high, right? So that's what we call the model is underfitting. On the other hand, if the model is too complex, we call it's overfitting. What does that mean? So look at that. The blue dots are the true observations, and if you make the model super complex to do something as crazy as this, of course it's doing a perfect job in the train set, but the problem is that this model does not generalize well. If you apply it to a test set, to a new data set, it's going to have very, very high variance, right? So, but the idea is that look at the bias though. Again, imagine I work with other subsamples. Let me use another color. And I use this super complex model. The idea is that on average, though, it's hitting at the target. So on average, it's capturing this nonlinearity. So it has low bias, but the problem is that the variance is super high. So it has, we are here now, it has low bias, but the variance is super high. And again, a combination of the two is going to be very high. So either we are underfitting or overfitting, we're in the wrong part of the curve. So what is the optimal? A good balance between bias and variance is somewhere in between, that on average you capture the true relationship in the data, and at the same time, if you work with different samples in the data, the variance is not that high. So the model variance is not that high. So you get a good mix of the two, and it's going to minimize your, for example here, your mean squared error in the test. Okay, so this is a balance between bias and variance in a nutshell. Another concept that I want you to be aware is, it's very similar to bias-variance trade-off, is something we call optimization versus generalization, right? So your model should be able to optimize well in the train set and at the same time to generalize well in the test set, right? So what I mean by that, so imagine we have something like this. I'm looking at cross-validation, let's say errors, and I'm looking at the performance in the train set and the test set, right? And I'm making the model more complex as I go from left to right, right? So in the train set, a good model is something like this that, so I'm going to look at, so the blue one is, so this is error, the blue one is train set error, and I'm going to use another color, the red one, for cross-validation error, right? So a good model is a model that can learn something if you make it more complex. So this is very, very important, because your model should be able to learn something. If you have a model like this, so for example, I'm going to go ahead and erase it later on, but if you have a model like this, no matter how complex you make the model, it's not reducing the error. It's not a good model. You have to do something about it, right? So a good model is a model that is able to optimize over the train set. So that's one thing. And the other thing is that the model should be able to generalize well as well. So it means that if I plot the cross-validation errors, the red one, it should be able to decrease. And of course, at some point, it will increase. So this is the part that the model is going to overfit. If I make the model too complex, it's going to perform very bad on the cross-validation set or in the test set. So this is a sign that your model is overfitting. And if the model is overfitting, you have to regularize it and go back a little bit, find the optimal value that's going to optimize the cross-validation error. This is really, really, really important. A good model is a model that can overfit. If your model cannot overfit, So if you plot the performance in a test set or a cross violations and you don't see this behavior, then it means that you don't have a good enough or flexible enough model in your hands. So you have to somehow do something about it. You have to change the structure of the model that you're using, right? Once you have a model that can overfit, this is good news. You can go ahead and prune it back or regularize it to make it less complex and to get to a point that it's able to generalize well as well in the cross-validation data or in the test data. I hope this idea is clear, and but be aware that a good model is a model that can overfit first place, and then in the second place, it's time to optimize it. It's time to make sure that it can generalize as well in the test set. Okay, so to recap the concepts of overfitting, overfitting happens when the fitted algorithm does not generalize well to new data. So this is an example for regression. Here's what we have overfitting, right? Again, it's doing a perfect job in a train set, but it does not generalize well in the test data, because if this is a test data, you can see the black dotted line or dashed line is not doing a good job at all. And this is an example for classification. Again, we are pushing it too much. The model is too complex, and we are unnecessarily capturing these things correctly in the train set, which we don't need it, right? This model does not generalize well. The model fits the train data too well while not predicting well in new data. So these are different versions of defining overfitting. The model fits the noise in training data, find a pattern that does not exist. So basically you're memorizing the pattern, right? So you can make the model super complex and memorize the data, memorize the pattern to get it, let's say, train error of 0. And the algorithm has simply, as I said, is memorizing the data rather than learning anything from the data. So it's not going to be generalizable. And this happens when your model is too complex. But again, don't get me wrong, it's not necessarily a bad thing. You want to make sure that your model is able to overfit. This is an important one. Once you get a model that is able to overfit, then you're going to regularize it back to make sure that it's less complex than what it should be. All right, so we said that having a model that overfit is not necessarily bad. Actually, we want to have that model, right? But let's say we have that model, how can we fix this overfitting part? There are different ways to do that. The first and most common one is collecting more data, okay? So for example, look at this. Let me use the right marker. Look at this data set here, right? We have 1, 2, 3, 4, 5 observations. If we have only these 5 observations, we can make the model complex and get this kind of pattern, right? However, if we collect more observations, which is going to fill the gap here, then we get to the next chart. This is a data set with more observations, and as you can see, the model is able to fit the data a lot better with a simpler model, right? So this is collecting more data. What I want you to be very careful is that collecting more data does not always work, and there's a reason for that, because what if your data that you're adding is simply just noisy and there's not much to learn from that data? So let me give you an example. Imagine you have, this is your error, and this is your model complexity. Okay, and you are doing, it seems you get something like this. No matter what you do, this is the performance of the model in the train set. Even in the train set, you cannot reduce the error as much as you want. So for example, this is your benchmark, or maybe lower than this. This is a benchmark, so this is benchmark error, and by no means you're getting close to that benchmark error, no matter how much you make this model complex. Guys, pay attention. This is a train set performance, right? Usually the train set performance should be something like this, right? But if you get something like this, it means that your data is not just getting it. The data is not informative in terms of explaining the target variable. So if that's the case, don't waste your time. Collecting more data is not going to help. So the next approach that we can combat this overfitting is what we just talked about, is right, some regularizations, complexity reduction. So for example, we go from this super polynomial model and we add some regularization terms. We're going to penalize this regression for having higher polynomial degrees, and it's going to make it to less complex by something like this, right? So these are different techniques. Again, one other techniques for complexity reduction is feature selection, basically engineering the features and come up with more informative features, hopefully to explain the target variable with simpler data. And then finally, we can always use our cross-validation and look at the performance in the cross-validation to come up with a better trade-off between bias and variance. So this is what we covered in the previous slide, right? So we use cross-validation, or in deep learning we do the validation set only sometimes, to figure out what is a better combination between the optimization versus generalization, between bias and variance, okay? All right, now let's quickly review the idea of partitioning the dataset in machine learning. I know you're quite familiar with this, so I'm going to speed up a little bit here. So what do we mean by partitioning? So we're going to partition the data. Ideally, we're going to partition it into three parts: the train part. The train set, validation set, and test set. Right? There is no right or wrong rule, but depending on the size of the data set, usually we do 70%, 70 to 80% train and validation, and 10 to 20% or 30% test set. But again, there is, depending on the size of the data, we can treat it differently. If you have millions of records of data, you don't need to keep 20% of it for test set. You can only keep 5% or 2%. But if you have thousands of data, you need 10 to 20% for the test set. Okay. So we use a train set to train the model, we use the validation set to validate it and tune the hyperparameters of the model, and we use a test set, so this is the most important one, to test the model's ability to see if it is generalized well or not, if it makes predictions, good predictions on the not ever seen data. Okay, so to be valid and useful, any supervised machine learning models must generalize well, so this is important, right? And beyond the train set. And now the point is, what if we don't have the large data set? What if we don't have millions of records of data that we can simply have enough information in the train set, enough information in the validation set, and enough data in the test set? What if that's not the case? And in so many machine learning examples and in the industry problem, that's the case. We don't have unlimited data. So how we do? All right, so what is this resampling method? So we know that we're talking about if this data set is small, and we want to divide it into train and validation, right? If the train set is small, the model is not going to learn anything. If the validation set is small, the model is not going to be able to do a good hyperparameter optimization. It's not able to tune the hyperparameters properly. And we will see that in practice, the model performance in the validation set is going to be very unstable. It means that if you do it for different validation sets, you're going to get very different performance metrics. The variance of the performance metric is going to be large. So what is the solution? The solution is combining these two sets together and use a technique called cross-validation. Okay, so the most common techniques in creating cross-validation is called k-fold cross-validation, and the idea is pretty straightforward. And the thing is that you're going to divide the train data into k roughly equal size and non-overlapping groups, right? And so let's say k is equal to 5 in this example. So I'm going to divide the data set, the ones excluding the test set, right, into 5 parts: 1, 2, 3, 4, 5, right? And then I'm going to hold k minus 1 part, 4 parts as a train set, and 1 part as a validation set, right? And I'm going to repeat this process for every single time that we have a separate validation set. So if k is equal to 5, so I'm going to have 1, 2, 3, 4, 5 different iterations, right? So for example, here the model is going to be trained on these 4 folds and make predictions on this fold. Here the model is going to be trained on these 4 folds and trained on this fold, right? And in terms of the performance, we're going to aggregate over all the performances, right? So for example, if it is regression, we're looking at the R-squared or mean squared error. We can simply go ahead and aggregate. As you can see, this method is going to be a lot more stable compared to doing this only once. But at the same time, if it happens that you have a very small data set, right? So you have a very small data set and you want a high accuracy. The problem is that you do cross-validation and you realize that the variance of these performance metrics, let's say MSE in the cross-validation, is high. If the variance is high, it means that whatever you're doing in the validation set, the performance is very different each time. So there's a solution to that, which is called iterative k-fold cross-validation, and it's specifically designed to come up with a more stable path for cross-validation, right? And again, that idea is very simple as well. The thing is that you can repeat this entire process p times and call it iterative k-fold cross-validation. As you can see, you can get more stable path for cross-validation performance, but the problem is that it is very high, it is very costly because cross-validation itself is computationally expensive. If you want to do p iteration of that, it's going to be even more computationally expensive. But I just wanted to be aware that there are methods to work with very small data sets to get a stable cross-validation performance. All right, to wrap up this part, let's talk about why do we use cross-validation. So we use cross-validation in practice for two main reasons. The first one is model architecture selection. So this is the idea of optimization versus generalization that we already discussed, right? So the idea is that, okay, which one is the case? If you're talking about simple polynomial regression model, is this a right model, or is this a right model, or is this a right model, right? So and the way that we figured it out is we plotted cross-validated error versus model complexity, let's say polynomial degree, and we realize that it behaves something like this. This is going to be my optimal polynomial degree, and maybe this is the answer. Okay, so that's the first reason we use cross-validation. Model architecture selection. Within the same family of models, what is the best set of hyperparameters? If it is linear regression, what is the best set of hyperparameters? If it is random forest, what is the best set of hyperparameters? The second reason for using cross-validation is to get a fair estimate of the model performance in a test set, right? Because after all, when we are doing cross-validation, let's say 5 folds, 1, 2, 3, 4, we are training on these 4 and making a prediction on the fifth fold, which is a validation set. So if we do not overkill this process of cross-validation, it is a fair estimate of the performance of the model in a test set, in a set that the model has not seen those observations. But this comes with a caveat. If you overkill this process, if you do the cross-validation a lot, so there's going to be a data leakage from validation set to the model, and this is a big if, because it's going to overfit. If your model is overfit in the validation set, then you're going to get fake good performance, right? So you have to be careful. So once we train the model in the train set, once we come up with a best architecture of the model using cross-validation, it's time to make prediction in a test set, right? So we estimate the generalization error or test set error using the test set. And then we're going to compare different families of models using the performance in the test set, right? So for example, at the end of the day, I have 4 or 5 different families of model: linear regression, logistic regression, random forest, XGBoost, you name it. The way that I compare these models with each other is based on their performance on the test set, not the cross-validation set. I hope that this is clear. What is the difference between why do we use cross-validation, and when we use the performance of the model in the test set. All right, before we move on to the solvers and optimizers part, so let's talk about yet another curve that's going to help us to answer this question. Do we need to collect more data, right? So this is called learning curve, and it's very important, and it's a very intuitive one. A learning curve is a plot that shows the relationship between the training set size from one hand and the performance of the model from the other hand, okay? It is basically used to diagnose that if your model is going to have a high bias, high variance, or it's just fine, it has the right combination of the two, right? So let me give you an example. Imagine, so this is a very important one, pay attention, because this is usually confusing for students to understand. So imagine this is your model, okay? So your model is a very simple quadratic function. Let's say y is equal to, it's very simple, just x1, and this is your y. Y is equal to, let's say, some bias term plus w1 x1 plus w2 x1 squared. Very simple model with some noise, right? If this is the model. Now I'm going to say, okay, this is the model. Now if the train size is just, let's say this is the only train size, right? And that's your model. Your model is perfectly capturing that one if you only have 2 observations. So if you're here, let's say 2 observations, if I have two observations, the error is 0, right? Because the model is going through those points in the train set and it's doing a perfect job, right? However, not surprisingly, the performance, so this was the performance in the train set. The performance in the cross-validation set or in the test set, it's going to be way worse, right? Because maybe in the cross-validation, we had observations like this. And we know that this model is not capturing anything, right? So the performance in the cross-validation set when the observation number is small, it's going to be very, very bad. Okay. Now let's start increasing the number of observations, right? So let's say we add a bunch of more observations. We get something like this. Okay. And now as we increase the train size, of course, the performance of the model is going to get worse because now we have more information and the model needs to fit the more information. And I want you to focus on the blue ones here only. Let me erase this one. Just the model needs to focus on more information and maybe it's not necessarily doing a good job for these observations, right? So what it means that the error is going to increase. Your measure of performance in terms of error is going to increase as the train set size increase because it's going to have harder time to fit the model. But on the other hand, this error is going to decrease for the test set or for the cross-validation, right? Because again, if this is a cross-validation data, it's going to be a lot better than this because we have more information now. I'm sorry. So we get to a point that these two curves are going to converge, right? Now you have to look at the your benchmark performance, right? Or we also call it common sense performance. Imagine this is your benchmark performance. If your model is not able to predict well for large size in the train set, even for the train set, right? So if your model is not outbidding the benchmark performance even in the train set, it means that your model is suffering from a large bias. So the bias is high. No matter how many iterations you do, no matter how large the sample size is, on average, your model is not hitting at the target. You know what? Maybe the target was something like this. Maybe the model needs to be polynomial to the degree of 3, right? So that's where you figure out that, okay, this distance is high. It's not outbidding or it's not bidding your benchmark performance, but they're converging to each other. So it means that you have a high bias problem. Okay, so that's a high bias problem. What is the high variance problem? High variance problem happens when the gap between this performance metrics between validation sets and train set is large, and it remains large no matter how much you increase the train set size, right? So let me give you another example to make sure that you understand why this gap may remain large. So here we say, let's say, our true model is good, and actually it's, let's say, using the same observations from the previous example. Imagine we got the right model. It should be something like this, right? Y and X. But the problem is that this is your train observation. This is your maybe cross-validation observations. So maybe we get some observations here, right? So it seems that in cross-validated, the model is not capturing the performance well, simply because we don't have enough observations, right? If we keep adding more observations, right, if we go to the right, these two curves should converge eventually. We should get to a point, something like this. So if the gap is large, this is a sign that your model has high variance, and we can fix it by collecting more information. Okay, so and when it is when you plot the learning curve, a just right model is, let me actually show it to you. So what is a just right model? So you have the cross-validation score that decrease relatively fast, and then the train score that increase relatively again fast, and for a decent amount of data we are outbidding the benchmark as well. Hopefully we're outbidding the benchmark as well. So this is a just right fit between bias and variance. Okay, so that was the learning curve. We are finally ready to answer this interesting question of how do machines actually learn. So at a very high level, we know that, imagine this is our machine learning box. We have some inputs, we have the labels, the model learns the patterns and makes some predictions. At the end of the day, we're going to compare these predictions with each other, and then try to optimize the weights and coefficients of the model, that this performance metrics is going to become better and better and better. So in a nutshell, to answer this question, how do machines actually learn is by optimizing or minimizing the cost function. And what is the cost? The difference, the distance between actuals versus predictions. Okay, now let's look at the formal definitions. Okay, so starting by learning, what do we mean by learning? Learning is this process of finding the model's weights and or the value of the parameters and hyperparameter. What is the cost function? Cost function tells us how good or bad the model is at making predictions given a set of parameters and hyperparameters, right? And so each cost function has its own curvature and its own gradients. And the slope of the gradient, well, basically, gradient is the slope, right? The sign of this gradient is going to tell us how we should update the parameters to make the model more accurate. So very naively speaking, imagine this is the parameter of interest that I'm optimizing over. Let's show it with theta. And this is my cost function. Let's show it with j of, it's a function of inputs and theta. And imagine it's very simple, something like this, right? And at each point, I can go ahead and calculate the slope. So here, for example, the slope is positive. If the slope is positive and we're doing a minimization, where should I go, left or right? Yeah, I should go left, right? So I go to the next point, next point, next point, and hopefully I get to the minimum. If I start from here, look at the slope. The slope is negative. So where should I go? To the left or right? The answer is right. So as you can see in this very simple example, we are going in the opposite direction of the sign of the slope, right? And so we're going to formalize it more mathematically. But so in general, there are two most frequently used optimization algorithms, and they are namely called gradient descent and stochastic gradient descent. So let's see what is gradient descent, and later on why we have to extend it and go beyond gradient descent and use something called stochastic gradient descent. All right, so let's start by the gradient descent definition. It's an iterative optimization algorithm, right, for finding the minimum of a function. So we know that no matter how we define the cost function, we want to minimize it, right? And hopefully, as the name suggests, we want to decrease the gradients along the way. Hopefully, we get to a point that the gradient is equal to 0, right? So we start at some random points and take steps proportional to the negative of the gradient, to the opposite direction of the gradient. And here is the mathematical formulation. So we have theta. Theta is our parameter of interest. And then we have alpha. This is what we call the learning rate. What are the magnitude of the steps that we go to the right directions? And then finally, this is our cost function, and this is the gradient of the cost function, right? So again, if I want to show you visually, I have this function, the cost function of x and theta, and then this is my parameter of interest. Imagine this is our very simple cost function. We are assuming that it is continuous and it's very well behaved, right? And then we start from random points. If I start from this random point, then I calculate the gradient. It's a number. Let's say it's +1. It's a number. I plug this number here in the gradient, and then I multiply it to something called learning rate. Let's say learning rate is 0.5. So alpha multiplied that gradient, this is 0.5. So I get minus 0.5 here, minus 0.5. And imagine your initial value for theta, again, naively speaking, let's say we start from number 4. So we do 4 minus 0.5, we get 3.5. So we get to this point, 3.5. And we keep repeating this process, right? We keep repeating this process, we get to a point that, let's say at this point, this is equal to 2, and the gradient is equal to 0, right? So we say, okay, if I want to optimize the theta, theta is going to be equal to 2 minus my alpha, 0.5, multiply the gradient, which is 0, it's going to be 2. So I will get stuck here. So this is the optimal value. The same story happens if I start from this random point. Again, the slope is going to be now, let's say, -1. I need to, and let's say, again, just for the sake of argument, imagine this is point, I don't know, 1 or 0.5, whatever. And then I say, okay, the new theta is going to be 1 minus the learning rate, 0.5, multiply the gradient, which is -1. So I'm going to get 1.5. So as you can see, we're going in the opposite direction, 1.5. Yeah, these are just, I use very simple numbers. In reality, it might be a little different. The steps are not necessarily symmetric, and etc., depending on the size of the shape of the cost function. Okay, hopefully it gives you a sense that how gradient descent at the very high level is working. All right, now let's talk about the choice of learning rate alpha. Well, if this alpha that we're talking about, the learning rate, is too small, what's the problem? The problem is that the gradient descent can be very slow. I want you to focus on this chart. And again, theta versus your loss function. A small learning rate requires many updates before reaching the minimum points, right? So for example, we go from here to here, and as you can see, it requires a lot of iteration. And the problem is that each iteration is using the entire train set to update the parameters. And if the train set is millions of records of data, so and if the model requires so many of these iterations to get to the minimum point, as you can see, it's going to be computationally expensive, right? On the other hand, if the alpha is too large, then the gradient descent can even diverge. We say it can jump over the minimum, or it can even diverge. So let's say, let me show you an example that it can jump. So for example, we start from here, and then imagine alpha is very large, and instead of going this way, we go this way. So we pass the minimum, right? We pass the minimum, and this is a problem. And sometimes the alpha is so large that instead of going even in the right direction, we go completely in the wrong direction. We diverge. So that's a problem of a too high alpha or learning rate. So hopefully we have to figure out what is just right or optimal level of alpha. With the smallest number of iterations, we get to the point that the gradient is equal to 0. Okay, now the question is, why should we go beyond gradient descent, right? There are some important disadvantages of gradient descent that makes us wonder, can we do it even better? And the answer is yes. So what are the disadvantages? First of all, and I think this is one of the most important one, is that the gradient descent is single batch. So what it means that it's going to use the entire train set to update the parameter. So as I said in the previous slide, if I want to go from here to here, the gradient descent is going to apply the entire train set here at this point, right? So, and if the data set is large, each step is going to use the entire train set, and obviously it's going to be slow. The second problem that we just talked about is that it is sensitive to the learning rate, right? So finding that learning rate itself is going to be expensive. And obviously a combination of two is that it's going to be slow for large data sets, right? So what is the solution? The solution is something called a stochastic gradient descent, or in a more general term, mini batch gradient descent. So the idea is a mini batch gradient descent is that it's a version of the gradient descent algorithm that it speeds up the computation by approximating the gradients. So it's not going to calculate the exact gradient, which is based on the entire data set. It's going to use a subset of data sets and basically try to calculate the gradients based on the subset of the data set. So it's going to approximate the exact value of gradient, right? So using smaller batches. So this is the idea of mini batch stochastic gradient descent. So it means that in this iteration, let's say we're here, I'm not going to imagine your train set has 1 million observations. This is train. And in gradient descent, I'm going to use all the 1 million observations to get an update. Go from here to here, to go from this theta to this theta. Now, in a stochastic gradient descent or in mini batch gradient descent, I'm not going to use 1 million. I'm going to use a batch of that, let's say 1,000. So I'm going to use 1,000 random observations from 1 million observations and then make an update. So this update is not going to be as accurate as the previous one because we're using fewer samples, obviously, but it's a good approximation of that gradient, right? So that's the whole point of batch gradient descent. So what is the difference between batch or maybe mini batch gradient descent and stochastic gradient descent? In mini batch gradient descent, the batch size is larger than 1. So obviously you have more than one observation, let's say 2, 10, 1,000 as in this example. In a stochastic gradient descent, the batch size, let me actually use a other color, the batch size is equal to 1. So this means that at each iteration, we are only using one random observations from the train set to update the parameters. As you can guess, it's going to be a lot faster, at the same time a lot noisier. So let's see in the next slide, let's see how we can visualize this. And by the way, stochastic gradient descent has its own different upgrades. So we're gonna talk about it in the following slides. Okay, so here's the picture that I was referring to. It's a very intuitive one. Imagine this is our cost function, and we only have two parameters, and I don't know, you can call it theta 1, theta 2, theta 1, and this is our theta 2, right? And then this is the cost function. We can look at different contours, right? And visualize it like this. So obviously here is the minimum point. Let me use yellow, you see it. So this is the minimum point, and the goal is to get into that minimum point, right? The blue one is our batch gradient descent, and let's say the batch size is the entire train set. So I'm using the entire train set here. I start from a random point. Let's say we start from this random point. And we use the entire train set. We find the right direction going down these counters, or going down the surface of the cost function. And because we're using the entire train set, this is going to be accurate approximation of the gradient, right? So we know the exact size and magnitude of the direction of the gradient, and we go along that direction, the opposite of that direction, right? Then we repeat this process, and as you can see, this batch gradient descent, or using the entire train set gradient descent, is going to be very stable because it is clear that at each point where direction should we go, because we're using the entire data set. The mini batch, let's say we start from here, I don't know, maybe we start from this point, it's going to be the less stable, but at the same time it's not that awful because we're using, I don't know, maybe hundreds or thousands of this training set. So sometimes it goes in not necessarily the right direction. So here, look at that, it's going in the wrong direction actually, but it's going to fix it up quickly because again, these are better approximations of the gradient compared to purely a stochastic gradient descent. Eventually we're going to get there, right? And then finally, for the stochastic gradient descent, let's say we start from here, the problem with that is even at the very first point, we can go in the wrong direction. And that's a problem because we're working with only one sample from the train set. So the bad news is that it's not going to be stable, but the good news is that it will get there. It will get there because, again, this is random sampling, and hopefully we get enough good random numbers down the road that can lead us to the optimal value for gradient, right? So what is the plus side? It's going to be super fast, super fast, because for each update, we only need one observation, and this is very key. Okay, all right, and as long as your cost function is continuous and differentiable, let's say it's well behaved, this stochastic gradient descent is going to work, right? And of course, but sometimes, again, in machine learning, the cost functions are usually well behaved, right? But in neural networks and deep learning, the cost functions are not as simple as this, right? So there are going to be, in the later parts in the course, we are going to visualize some of the cost functions in neural networks, and it's going to be super noisy. You know, this is something like that. It's a surface like this, and then you're trying to minimize over this. So for that, we need to go even beyond a stochastic gradient descent. So the idea is that why we should go even beyond this stochastic gradient descent is usually for deep learning. When the loss function is not necessarily well behaved, it's difficult to optimize. So here is a paper that visualized the loss landscape of neural networks, and as you can see, it is very noisy, right? And we have so many local minimums all around the place, and hopefully we are trying to get to this global minimum, right? So it's going to be difficult to get there because imagine, let me actually visualize it in two-dimensional space. Imagine we have something like this, right? And if I start from here, and if I use gradient descent, batch gradient descent, mini batch, or stochastic gradient descent, the algorithm will get stuck here because at this point the gradient is equal to 0, no update. If I start from here, the algorithm is going to get stuck here. If I'm lucky and it starts from here or here, I get to the global minimum. But how can we fix this? So the way to fix this is by designing an adaptive learning rate, right? So this learning rate should work in a way that it adapts to the loss landscape, right? So for example, it needs to incorporate the previous values of gradients as well, right? So we call this momentum. So rather than just looking at the current gradient, it needs to take into account the previous weights updates as well, right? So for example, if you're doing something like this, if the gradient is, I don't know, here's high, it's going to take larger steps, here's going to take smaller steps, but at the same time, it's going to take into account the previous weight updates. It's going to give this thing, imagine of it as a rolling ball down the hill, enough momentum to pass this local minimum and then go to the global minimum. So that's the idea at a very high level and in a very nutshell. So this is a point of what we call momentum, and it's a very effective way to for finding the global minimum in neural networks. So these extensions that using momentum, there are different versions of them, namely Atom, AdaDelta, AdaGrad, and RMS-Prop. So these are the more commonly used, especially the RMS-Prop and Atom when it comes to optimizing the loss function for neural networks. But for machine learning algorithm, usually the cost functions are very well behaved or compared to this ones, and the stochastic gradient descent should just work fine. All right, now I think we have all the moving part of this puzzle. Now we can put it together and see how do machines actually learn. So this is a very important part of this video. It's actually the last slide. I want you to pay very good attention. So what do we do? As a researcher, we have a research question in hand, we have some interesting hypotheses, we collect data, and we start to build a model and see how that model make predictions, right? So step one, we are going to actually, let me plot our black box. This is our machine learning thing. And there are some inputs. The inputs are X's and Y's. And if it is a supervised learning model, right? And I'm going to divide it into three parts. Train, test, split. If the data set, train, test, and validation. If the data set is small, we're going to do train, test, and divide the train into using cross-validation, right? And then we are going to come up with a structure for the model. Depending on the type of the data, we use different architecture. So for example, if you're dealing with a structured data, we can do linear regression, we can do random forest, we can do XGBoost, we can do KNN, different machine learning models. If it is unstructured data, we know that we would be better off using neural networks or some deep learning models, right? So whatever it is, we are saying that, okay, this is the architecture of the model. It's a function of inputs and the parameters of the model. The parameters can be the weights, can be the hyperparameters, and etc. Okay. The next step is to initialize these values for parameters and hyperparameters, and we do it randomly. So random initialization. So we say, okay, W can be some random stuff, random numbers. The hyperparameters can be some random numbers, and then with that, let's go ahead and use a train set and start training the data, training the model, right? So how do we do that? By using these values, we're going to come up with some predictions, right? Because remember, we do have the weights now. It's a random number. Based on those weights, I can apply it, use the original data X, and come up with some predictions, Y hat, right? So we make predictions in a train set and validation set. And at this stage, we don't make prediction on the test set yet. It's too soon, right? Because we haven't optimized the model yet. So then we have these predictions, we have the actuals. With predictions and actual, we are going to look at some performance matrices, right? So for example, we look at MSE in regression, we look at accuracy in classification, and etc. Right? So we now have a sense of what is the performance of the model in the train set, in the validation set, right? So at this point, the model should perform very poorly because why? Because we started these weights randomly, right? So this is obviously not the answer to the model, right? So it's time to optimize those weights. How do we optimize those weights? We're going to use, again, if it is machine learning, well-behaved cost function, we can do gradient descent. If you want to speed it up, we can do a stochastic gradient descent. If it is giving you a hard time kind of functions, cost function, we have to use some more advanced solvers like Atom or RMS-Prop, right? So, but in either case, at this point, I want you to pay attention. These happen simultaneously. This is step number 7. the optimizers, the solvers, update the parameters, these weights and these, let's say just only the weights of the model using the train sets, right? So this is the learning part. This is what we call the model is learning something, is learning those weights, right? At the same time, pay attention here, we're updating the hyperparameters of the model using a validation set. And again, if the data set is small, using cross-validation or iterative cross-validation, k-fold cross-validation, right? But anyhow, at the end of this step, at the end of step 7, we have an optimized version of the weights here, right? So this is iteration number 1. So the weights have been updated, the hyperparameters, let me show them with D, have been updated as well. We're going to go through this process one more time. And then look at the performance. If you're happy, we move on to the next step. If you're not happy, we iterate through this thing, okay? Until we get to a point that we are satisfied with the performance of the model in the cross-validation set, right? After that, we go to the last step, which is, okay, let's go ahead and look at the performance of the model and see how we can deploy it in the wild world. And hopefully your model is generalizable. It means that it performs decently in a data that has never seen before, right? So this generalization is key. So the end goal of machine learning is to come up with a model that can generalize well, that can make predictions on the never seen data. All right, that's pretty much it. We're done with part 1, machine learning for time series forecasting, the basics. Now you should have a very good idea of how we can transform a time series data set and pre-process it, prepare it for a supervised machine learning task. And then you should be quite familiar with all the terminologies and things you need to know from machine learning fundamentals, and you're ready to dive deeper into more advanced machine learning models for time series tasks, namely, again, the decision tree base. I will cover simple decision tree because that's the core model of all these things. And then we are going to go to random forest, then XGBoost, CatBoost, and LightGBM. And again, I'm repeating myself, we are using these models only in this course simply because when it comes to a time series task, these are the better performing machine learning models. Yeah, that's pretty much it. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.